Thunderstorms are mesoscale convective systems that are classified based on the number, organization, and intensity of their constituent cells. So there's two basic types. There's single-cell thunderstorms. These are usually weak system forming along a boundary with an air mass, like a gust front. And they typically last about 30 minutes or less. The second type are multicellular thunderstorms. These characterize most of the thunderstorms that we experience. Each cell may be at a different stage in its life cycle, and so we have an ongoing system that can last for quite a while. There are a couple of types of multicellular thunderstorms, and we'll talk about each one, starting with the squall line. A squall line is an elongated cluster of thunderstorm cells with continuous gust front at the leading edge of typically a cold front. So here's a picture, radar image, that shows a squall line, and you can see by the intense line here of thunderstorm development. These are typically associated with a mature mid-latitude cyclone, like we spoke about in a previous chapter, which are these big comma-shaped storm systems that we get. We don't see the satellite imagery here, we're just seeing the radar, so we don't see all the cloud cover, but we definitely see the cold front here, and right out front of it is the squall line of intense thunderstorms. The second type of multicellular thunderstorms is called a mesocyclone convective complex, MCC, and these are nearly circular clusters of multiple interacting thunderstorm cells. They can last anywhere from 6 to 24 hours, and they typically happen during the warm season in North America, from March to September. They often develop at night over the eastern two-thirds of the United States. They're not associated with a front, but they are associated with conditions that are denoted with a weak synoptic scale flow. Synoptic scale, remember, is 60 to 6,000 miles and lasts on the period of days. So maybe like a stationary front, for example. And they often develop near an upper level ridge of high pressure on the cool side of a stationary front. And we typically have a low-level jet that's feeding warm, humid air into the system. So here you see a satellite image and a radar image compiled showing an MCC over the central portion of the United States, and you see the circular formation, the intense thunderstorm activity denoted by the red colors, and you can see there's a supply of warm, moist air here. No doubt this low-level jet is feeding this storm system. A third classification of thunderstorms is something called a supercell thunderstorm. It's a single cell, but it's a very intense, long-lived single cell with an exceptionally strong updraft and a cell that has taken on some rotational circulation. These guys often develop into tornadoes. So here's a picture of a supercell. You can see just a very ominous-looking thunderstorm, and you can see that it's taken on some rotational movement here. So here's a schematic of a supercell. We have our cumulonimbus cloud, so we've got the updraft and then the downdraft and a demarcation between drier air and moister air. So there's a real difference in density within this cloud. And when we have the downdraft come down, we can get this gust front kind of thing happen out front that can produce what's called the roll cloud. And these clouds become just kind of monsters of their own. So we can get some rotation down here at the surface, and we can also get some rotation happening within the cloud itself. We'll look more at these as we talk about tornadoes a little bit later in this chapter. Thunderstorms happen anytime conditions are ripe. So what are those conditions? One of them is humid air in the low to mid troposphere. Oftentimes this is maritime tropical air mass, so it's a moist tropical air mass that causes the atmosphere to become destabilized. So that warm, moist air sitting underneath relatively cooler air aloft causes instability and convection to happen. So the warm, moist air lifts up to the convective condensation level. We get clouds forming, And if there's any source of uplift, in addition to this regular convection that happens from radiational heating, like a mountain slope or convergence of surface winds or along a front, then we're definitely likely to see thunderstorms develop. Solar heating drives atmospheric convection. Solar heating drives weather, period, and in this case it drives convection. So thunderstorms are most frequent when and where solar radiation is most intense. And also storms are most frequent during the warmest part of the day. So when and where is solar radiation most intense? Well, go back to chapter 3 when we talked about Earth-Sun geometry, and we know that on a global scale, solar radiation is most intense around the equator. And then we have our seasons. So for North America, for us, it's going to be most intense in the summer when it's warm. And then in that big picture, if we look at the smaller picture of what's happening during the day, thunderstorms are most frequent when it's the warmest part of the day. And all of that warm air is encouraged to lift up and form clouds that can develop into cumulonimbus clouds and thunderstorms. There's lots of exceptions to this. One example that the book talks about is the low-level jet stream that goes up the Missouri-Mississippi River Valley at night that contributes to nocturnal thunderstorm maximum activity. So there you get nighttime thunderstorms. Thunderstorm frequency is often expressed in thunderstorm days per year. It's just a count of the number of days in which thunder is heard. So it depends on somebody hearing that thunder. So it underestimates what's going on. Here's a map that shows the number of thunderstorms annually. You can see these isolines represent that quantity, the number of thunderstorms annually. In our country, the most being in Florida. The book talks about the Florida Peninsula as a hotspot for thunderstorm development because it's a narrow peninsula in a subtropical area. So we get sea breezes blowing from either side that cause air to converge and lift up, and this is maritime tropical air masses, so it doesn't take much to destabilize and form into thunderstorms. So we get our maximum thunderstorm activity in Florida, and it kind of radiates out from there, really. So over here in Arizona, we have most of our thunderstorm activity in the southeastern portion of the state, and it decreases as we move westward. We'll talk about some of the different phenomena associated with thunderstorms in the next part of the lecture. Bye for now.